The sum of products min-term form expressions are a great way to compactly and efficiently communicate when a particular circuit or piece of digital logic is going to produce a 1 for output versus a 0. What's also nice about this form is that we can trivially translate it into the sum of products form. That was the form where for each min-term that produced a 1, we had a variable product, and then we ORed that with the next variable product, ORed with the next, and so on. And that translates directly into a circuit that has a nice layer of AND gates followed by a single OR gate. All of this is great, but that long sum of products form expression translates also to a long layer of AND gates. And so what we want to do is maintain this translation, but somehow make the circuits more simplified. And so that's what we're going to look at today using a technique called Karnaugh mapping. But before we get to what a Karnaugh map is, let's take a look at our recent favorite bizarre expression. So here is our function z, which is the NOR of a and c, ORed with the inverse of b ANDed with c, exclusive ORed with a. Right? We converted this to a truth table, and from the truth table we could derive the sum of products min-term form expression. And this is translated directly into this sum of products expression. So here we see the min-term 0 represented by this product, where A has an inversion bar, B has an inversion bar, and C has an inversion bar, meaning we're looking for a 0 on A, a 0 on B, and a 0 on C. That's in contrast to, say, here, this product where we don't have an inversion bar over A, which means we're interested in a 1 here, and a 0 here, which is the bit pattern in 3 bits for the number 4. So the fourth 4 min term from here correlates directly to this term. This is a very long expression, but we want to keep a products and sums style form. We just don't want the complete sum of products form if there is a way to simplify this so that it performs the same function. So what I can tell you is, without showing you how yet, is that we can actually reduce this down to a different expression. We can reduce this to A and B ORed with the inverse of A ANDed with the inverse of B ORed with the inverse of C. And we can go back and see how this is feasible, because what I'm going to do is I'll mark this up for us. In using blue, I'm going to identify up here the terms that relate directly to this, because you'll see what happens. We're missing in this product the variable C. So what I want to do is look for terms up here that have regular A and regular B ANDed together. And that's going to be these last two terms here. Regular A, B ANDed with the inverse of C. Regular A, B ANDed with the regular version of C. So effectively what this means is, if we looked at just these two blue terms as a part of a greater expression or greater circuit, we're saying A is a 1 and B is a 1 and C is a 0, or A is a 1 and B is a 1 and C is a 1. But really this means A and B are 1s and C is either a 0 or it's a 1, which is everything that it can be. So we're effectively saying A has to be a 1, B has to be a 1, and C is really of no consequence. And so we remove C here. So these two products can be converted into this more compact one, A, B. Now let's look at the same thing for the middle term. I'll do that in green, since I have a green marker handy. Now I'm looking for the inverse of A ANDed with the inverse of B. I see two terms here and here that have that particular quality. Again, notice that the variable C is missing from this product. Well, up here the C is in both products, and we have the same situation. This says A should be 0, B should be 0, and C should be 0, or A is 0, B is 0, and C is 1, which really means A and B should both be 0, and C can be either 0 or 1, which means it's inconsequential. so we remove it from the product. Now let's do that again for this last term that I have, because so far it's reasonable to see that these two terms combine to this, and these two terms combine to here. And we may be tempted to just take the remaining two products from the original sum of products expression and reduce them. But we want to get as compact as we possibly can. And if we looked at this, we would see that the only thing in common between this one and this one, these two products, is they both have the inverse of C. But that doesn't mean we can shrink right away to the inverse of C, because we need to see that those were combined with every combination possible of A and B. And since there are two variables, that requires 4 products. And there's not enough here with just these two. In fact, what we do is we use this one, and since I have said it's the inverse of C, we'll find all of those. Here's one here, and here's one here. Now, each of them have the inverse of C as a part of the product, but let's look at the bit patterns on A and B. So here's the bit pattern for 0, 0. Here's the bit pattern for 0, 1. Here's the bit pattern for 1, 0. And here's the bit pattern for 1, 1. So across these 4 products, even though those 4 products overlap both the green and blue, they still indicate to us that we want C to be inverted. And really, if C is inverted, it's of no consequence what A and B are. So we can get rid of A and B in this product here. Now that's pretty nice, and this is about as compact as we're going to get it, keeping it in a sum of products style, right? Because that will convert to a very nice circuit for us that'll be much cleaner, or at least much smaller than the circuit that's directly made out of this complete sum of products form expression. But let's see that we can also get here directly, since I wrote this and then reversed our way back, let's see that we can actually go from this to here in general. This technique that I used of grouping things works generally speaking. So let's say we have just 2 variables, A and B. So I've got A and let's say the inverse of B, ORed with A and regular B. Okay, so that's what we're going to start with. If I go back and look at my logical equivalence laws, what I can do is use distribution to pull the A out, or to group things by the A and say, this is the same as A ANDed with the inverse of B, ORed with regular B. And I get that through the distributive property, or distributive law, I'm sorry. Then I can look here and see that I've got this weird thing in parentheses where I say the inverse of B or regular B. Well, one of those is a 1, and 1 ORed with anything is definitely a 1. And so this is really the same then as A ANDed with 1. And that is the negation law. I think it's the AND OR form of the negation law. Now once I've got this, I can swap the two so that it says 1A, which will be the commutative law. Oops, I forgot my U. You can't see it well, but there's a U there, so commutative. And then I'll follow that by the identity law, and that gets rid of the 1 because anything ANDed with 1 is itself. So commutative and identity laws, one after the other. And then we have A. So what does this mean? Well, this means in general, if we have a variable, and then next to it we have another variable, and the first takes one form, and in its other products, the other variable takes all possible forms, one inverted, one not, we can, strictly speaking, just remove that variable because it has no consequence on the end result. Now, if this were A, B, and C, we could apply these steps to get rid of the B. And then if we needed to get rid of the C as well, the same set of steps would apply to what remained. So this generic approach that I've done here can be used universally to simplify our complete sum of products expressions into very nice compact sum of product expressions. What we're going to look at for the rest of this video is a technique called, or a tool called a Karnaugh map. And a Karnaugh map is just a way to visualize this process. So it simplifies the process of simplification. Because when we have very long, complete sum of product expressions, it's hard to evaluate whether or not this term and that other term all show up, so that we remove unneeded variables as best we possibly can. With the Karnaugh map, this becomes easy because we have a visual tool that makes it clear. All right, so a Karnaugh map is going to use 2 to 4 variable truth tables. And I know these don't look like truth tables right now. But Karnaugh maps take 2 to 4 variable truth tables and redraw them as 2-dimensional grids. Now, if we have more than 4 variables, here's a Karnaugh map for a 2-variable AB function. Here's one for 3-variable ABC, and here's the one for 4-variable A, B, C, and D. If we wanted to go beyond 4 variables, we would have to add more dimensions. We would not extend any one dimension to be further than you see in these diagrams. We'd have to get hyperdimensional, which is pretty hard to do on paper, but not so hard to do in code. So we can write software to do this for us. But for us, we'll stick to 2 to 4 variable truth tables and redraw them in 2-dimensional grids. Now, the way these 2-dimensional grids work, we can look at each one, is along each dimension are 1 or more variables. So in the top left, the vertical dimension is the variable A, which can go between the values 0 and 1. And the horizontal dimension is for the variable B, which can have the variable values 0 or 1. We have the same vertical dimension here for this 3-variable function, but the Karnaugh map for it would have to extend horizontally, so that in this one dimension, we actually have variance over 2 variables, so B and C. And each of these 2-digit bit patterns that you see here represent a B and a C value. So this column means B is a 0, C is a 0. This column means B is a 1, C is a 1. And this column means B is a 1, C is a 0, and etc. for the other column. For the 4 variable functions, we make a 4 by 4 map. So it's got 16 places for us to have our 16 elements of the truth table. And in each of the 2 dimensions, we number them the same way we did the horizontal dimension up here. But the numbering, if you look carefully here, is a little different. So this is the 2-bit pattern for 0. This is the 2-bit pattern for 1. But this isn't the 2-bit pattern for 2. This is the 2-bit pattern for 3. And then comes the 2-bit pattern for 2. That's duplicated here and as you go down on this Karnaugh map. And the reason is because what we do is we effectively have made a way to represent an intersect between the 2 dimensions that means a multi-digit number equivalent to the midterm. In our simplest one over here, if I just pick this cell here, this is A is a 1 and B is a 0, so that's the bit pattern 1, 0, which is the same thing as the number 2. So given a truth table for a 2-input function, we would put the output for minterm 2 right here, whether it's a 1 or a 0. Same thing is going to happen over here. We've got 1 and 1, that's 3, or 0, 0, that's 0, or 0, 1, that's 1. So these, the positions in this 2-dimensional grid indicate which minterm we need to use. Now this one is totally reasonable, 0, 1, 0, 1, it's obvious. 0, 1 again over here, but why the weird ordering? Well, what we want to do is we want to ensure that when minterm outputs are placed in these 2D grids inside of these Karnaugh maps, we want to ensure that from wherever we are, if we take either a horizontal step, a single step, to the left or to the right, or a vertical step, up or down, and if we have to, we would wrap around to the other side, and that works horizontally as well, whenever we take a single step horizontally or vertically, that has to change exactly 1 bit in the min-term representation. So if we pick cell 5 here for min-term 5, it's the bit pattern 101. If I go to the left 1, I get 1 bit of difference because I don't have 101, I've got 100. If I go to the right, the middle bit changes. If I go up 1, the leftmost bit changes. And that's going to be true for every one of these cells. You can look through that later to understand that it is. Now, the way we accomplish this is by numbering or labeling each of our dimensions using something called gray code. In gray codes, each consecutive bit pattern differs by only a single bit. So 0, 0 is different from 0, 1 by 1 bit. 0, 1 is different from 1, 1 by 1 bit. And 1, 1 is different from 1, 0 by 1 bit. And if we wrapped around, 1, 0 is different from 0, 0 by only 1 bit. So we just have to remember that this will always sort of be labeled 0, 1, and then skip over for 2 and come back for 3. Same thing's true here. 0, 1, skip a row to get down to the 2, come back up for the 2-bit representation of 3. It works horizontally and vertically. So in this big one, if I pick some place like 13, there's no obvious relationship between 13 and the numbers 12 and 15, 5 and 9. But if we look at their 4-bit patterns, as I move to the left from 1101, the rightmost bit changes. If I go to the right, the second to last bit changes. If I go down, second to first bit changes, or I guess the second bit changes. If I go up, the very first bit changes, the highest order bit. So the same basic thing here. So we're taking a truth table, and we're not making, for example, a 16-row table. Instead, we're making a 4x4 grid that can hold 16 zeros or ones, and we put into each of these cells a 0 or 1 based on the min-term row that the position represents. Right? This is the basic layout. Now, I know you might need to copy this down, so we'll do a quick freeze frame so that you can copy this down for your own needs. Okay. Oh, that's a horrible joke. Not even remotely funny. But it made me feel good in my office all alone. All right. So, let us look back at our crazy function again. So here is our weird function. The one for which we found the sum of products, or the sum of min-terms 0, 1, 2, 4, 6, and 7 to represent the truth table adequately. So what I've done here, since this is a 3-input function, is I've drawn out a 3-input Karnaugh map. I've labeled one dimension A, the other dimension is B and C. I've labeled it intuitively here, 0, then 1, with the origin kind of in the top left. And then over here I've labeled this one with gray code, where every column has a 2-bit pattern that differs only by 1 from the previous or the one that follows it. So 0, 0, 0, 1, 1, 1, 1, 0. Do not forget that gray code ordering, or you will not get the rest of what we're going to do to work. So if you look here, we sort of see these 2 zeros floating around, and then we've got all these 1s, and they're kind of clustered together, and that is good. Whenever the 1s are clustered together, we are going to get some value for this. Now, if you'll remember what we did before, we took this minimized equation that I gave you, expression that I gave you, and we found out why it was reasonable for it to be minimized in the way that I did it. We found all the different products that could be reduced to each of these 3. And once we reduced each product from the original complete sum of products expression at least once, then we knew we had full coverage down here in this expression. So here is that same expression, the reduced one, the simplified one. We're going to do the same thing we did before. But instead of marking the relationship from here to the complete sum of products, we're going to go from the simplified sum of products to the Karnaugh map. So now what I want to do is find all the cells that are in here that are represented by this product, A, B. This product really means A should be a 1 and B should be a 1 because neither have inversion bars. Inversion bar over something means we want a 0 there. So A is a 1, B is a 1. Well, A is a 1 in this bottom row. And B is a 1 whenever the 2-bit pattern has a 1 on the left. So that's here and here. So the last 2 columns have B as a 1. And I want to find everything where A is a 1 and B is a 1. So that's these 2 terms here. All right, now we'll do the same for A inverse ANDed with B inverse. So I'm looking for A is a 0 and B is a 0. A is a 0 in the top row, and B is a 0 here, and B is a 0 here. Otherwise, it's 1s. We don't care about C being a 0 or a 1 in this circumstance because C doesn't even exist in this product. It's of no consequence. So we can put a loop around the 2 terms that meet these conditions, or this condition. Then we'll do the last one. I did that in red before. Yeah, red. All right, for this last one, we're looking for all the situations in which C is a 0. So C is a 0 here in this column, and all the way on the other end, C is a 0. But don't forget, as we go off the map vertically or horizontally, we can wrap around, and we've maintained that pattern of the bits changing by only 1 bit. So if I go from this cell, which is the bit pattern 0, 1, 0, and wrap around to here, I'll have the bit pattern 0, 0, 0. So it only changed by 1 bit, the middle bit. Same be true if I go down. That's a fairly interesting thing. So what we can do is not group a group there and group a group here, but we're going to do one big rectangle like I've got here. It's just going to wrap around torally. So now I have really a 4-element rectangle here that includes all the ones matched up to here. And if we went and compared them back here, we would see the same overlap that we saw earlier in this lecture. All right. So this is again me working backwards from here to where does it map up. But in this case, compared to what we did before, this business, it's not so easy to look at this and figure out how many products we're going to get out of this kind of thing and what products they will be. But when we look at this one, at least in retrospect with the rectangles drawn, we can sort of see these visual clusters. And so we can start with this and actually get our way here pretty easily. And we do that with a process called ones looping. So we use a Karnaugh map to perform ones looping. And ones looping is a very simple process. It's one thing to go from here this way, but if we're going to start here, we need to follow certain rules. The first of these rules is that we put rectangles only around 1. So we're going to draw rectangles around 1s only. So we can't draw a rectangle that includes a single 0. Got to be only 1s in any given rectangle that we draw. That's absolutely critical, or the result we get in the end will be wrong. The second rule is that the area, at least for our 2 to 4 variable functions, for more we would go into hyperdimensions, and so it would really be a volume. The area of each rectangle needs to be a power of 2. Needs to be some integer power of 2. Now, another way that you can think of that is that the height and width individually also must be powers of 2. And since we're restricting ourselves to doing this on paper to those things that we can fit in a two-dimensional grid, the biggest dimension we've got is 4 big. So we're talking about rectangles where one of its dimensions, whether it's width or height, is either going to be 1, 2, or 4. That's the only ones we can get. And it doesn't have to be a square, as we've seen here. These can be rectangles. This red one is a square. But the whole area has to be a power of 2. And you'll always get that when each dimension is a power of 2. So if we were to see 3 ones in a row and the rest were all zeros, we couldn't put one loop around all 3, even though they were clustered together by putting rectangles around ones only. The reason would be because the height would be a power of 2, 1, but the width for a set of 3 ones would be 3, which is not a power of 2, so the total area would not be a power of 2. Now the last one, which isn't really a rule in terms of getting correct results, but is a rule in terms of simplifying this sum of products function as much as we possibly can, is that we want to cover, well, I guess this is half rule, half not. We want to cover, all ones. That by itself is critically important. This is rule. You must cover all ones, but we want to do it, this is the part that's rule of thumb, with as few big rectangles or loops. Some people call these loops. That's why we call it ones looping. So we have to cover all the ones. If we don't, we won't end up with enough products in the end when we convert from the looping to the products. We won't end up with enough products to actually cover all the times that our circuit needs to produce a 1 as output. However, we could have just looped each one by itself, but that's going to end up giving us the same thing as this sum of products in its complete form. If we make the fewest number of really big rectangles possible, we are going to get the most simplified sum of products expression. So let's work from here out as the last thing we do, just to see how we can get this done. So we know we have our function z as a function of a, b, and c. And we've done some a Karnaugh map where we filled it in from the truth table, and now we've done our looping and everything is covered, and our rectangles only cover ones, and they cover all the ones, and each rectangle has an area that is a power of 2. So now we just have to figure out what each one represents. I'm going to start with the red one since it's closest to the left here on the paper. So in this case I've got 4 ones here, 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 and here. And what I need to do is come up with a product based on the variables a, b, c that represent these 4 cells and no other cells. So I can see A, for example, to get to this one and this one, A has to be a 0. But A has to be a 1 to get to this cell and this cell, which are also part of this loop. So what does that mean? Well, it means A doesn't really determine whether I'm in this loop or not in any way at all. So A is not going to be a variable in this product. What about B? Well, these 2 ones happen when B is a 0. And these 2 ones happen when B is a 1. And since that bit changes within the same rectangle, that variable must be meaningless to this rectangle. So B and A are not part of this. So we'll look at C. Well, in this column, C is a 0. And in this column, C is a 0. So all of our ones in this rectangle are not influenced by A and B, but they are by C, specifically when C is a 0. So we're looking for the inverse of C for that one. That's going to get ORed with, say, this green one. All right, what's going on in the green one? Well, all of these 2 ones happen when A is a 0. So we need A to be a 0. What about B? Well, in this one, B is a 0, and this one, B is a 0. So that means B must be a 0. Okay, B is a 0. What about C? C is a 0 for this one. C is a 1 for this one in the rectangle. So the ones in this rectangle are not distinguished by C, so we're done with the variables for this product. We'll OR it with whatever the product is for the blue loop. Well, here, starting with A, these two ones that are inside this loop, all of the ones in this loop happen when A is a 1. So A, no inversion bar. B is a 1 for the first. For the second, B is a 1. So B is always a 1. B with no inversion bar. C, on the other hand, for these two, goes from a 0 to a 1. And since it could be either, that means it has no role to play, and we can eliminate it. Now that we're done identifying the products for each of these, we have found our simplified sum of products expression. So with the sum of products expression, we can, and a Karnaugh map, with a Karnaugh map, we can re-visualize any truth table for any circuit in such a way that ones can be clustered together in groups that we can outline, so long as those outlines meet certain conditions. Those rectangles meet those conditions we listed. And that will give us a way to write down a new sum of products expression that isn't complete, but it is simplified, removing extraneous variables from products that don't need them. Now, in an upcoming video, because I know this material is a lot to take in at once, in an upcoming video, we'll walk through a number of examples of doing this thing for circuits that we will either have seen before or are making up for the first time.